Here is a problem which deals with the relative motion analysis that we've talked about earlier. So an aircraft carrier, which is shown in the image, is traveling forward with a velocity of 50 kilometers per hour. At the instant shown, the plane at A has just taken off and reached a velocity v, which is horizontal, and has a value of 200 kilometers per hour measured from still water. Again, since we're dealing with still water, which is fixed, this measure is actually absolute. Now, if the plane B is traveling along the runway of the carrier, so it's still resting on the runway, at a speed of 175 kilometers an hour in the direction shown, what is the velocity of A with respect to B? And that's clearly VA with respect to B. So I'll give you a couple of minutes to try to solve this problem on your own, and when you're ready to see the solution, feel free to continue the video. So first we need to write down what we know. We have the velocity of the carrier, which is 50 kilometers an hour. We have the velocity of the plane A in absolute terms, which is 200 kilometers per hour. We have the velocity of B with respect to the carrier. Remember, the plane B is still lying on the carrier, so whatever velocity it has, it's the velocity with respect to the carrier, since the carrier is moving as well. And so VB with respect to the carrier is equal to 175 kilometers an hour. And we're asked to find VA with respect to B. We know that we're dealing with a 2D framework, so we have an I and J components, and that's because we're working in a single plane. We also know the equation for relative motion analysis, which states that in general, VA is equal to VB plus VA relative to B. And so if we're actually looking for VA relative to B, that's equal to VA in absolute terms minus VB in absolute terms. So the next step is to find VB. So we know that we have the relative motion equation. VA relative to B is equal to VA minus VB. We have VA. We're looking for VA relative to B, but VB is still unknown. So in order to get the final answer, we need to find a way to calculate VB in absolute terms. So writing the relative motion analysis again, for B, we have VB is equal to VB relative to the carrier plus the velocity of the carrier itself. So the first term is 175 kilometers an hour, but since we're dealing with a 2D framework, we need to split that into I and J components. We have selected the I component to be aligned with the horizontal axis, and that's the axis at which the carrier is moving and airplane A is moving. And so we get 175 cosine 15I, that's the projection of VB relative to the carrier onto the I axis, and 175 sine 15, the projection of VB relative to the carrier onto the J axis. And since the carrier is moving along the I axis, it only has a single component, which is 50I. Now summing the I components together and the J components together, we get VB is equal to 219.04I plus 45.293 J. Now that we have VB and VA both in absolute terms, we can calculate VA relative to B using the relative motion equation. So VA relative to B is equal to VA minus VB. Let us write VA in terms of the I and J components. Since the airplane A is moving along the I axis, we know that it only has a single component, which is 200I, minus the terms for VB, 219.04I minus 45.293J. And then adding the I components together and the J components together, we have VA relative to BX equals to minus 19.04, and VA relative to BY is equal to minus 45.293. Now to get the magnitude of VAB, it's simply the square root of the component squared, which is equal to 49.1 kilometers per hour. And to get the angle that the velocity VA relative to B forms with any of the axes, we can take tan inverse of VA relative to BY divided by VA relative to BX. And notice, since VA relative to BY, the Y component is on the numerator, we're actually calculating the angle of V with respect to the x-axis. And so we end up with a value of 67.2 degrees. Now, in order to draw accurately the vector VA relative to B, one needs to look at the x and y components, and mainly at their signs. So VA relative to BX is negative, and VA relative to BY is also negative. So the vector VA relative to B is oriented towards the left and the downward direction.